In the last video, we defined what it means to diagonalize a matrix. In this video, we just want to go ahead and do some examples of that. So here's problem 1, problem 1, part B. You'll do parts A, C, and D in your homework, so we're going to work the other ones here. All we're trying to do is, starting with the square matrix A, we want to turn it into a product of x, d, x inverse, where x is some invertible matrix X, and D is a diagonal matrix. Of course, if you paid attention in the last video, you know where the stuff in those matrices comes from, and it really just boils down to doing the eigenvalue problems that we're doing in 6.1. So that's all we're going to do. We're going to start off by finding eigenvalues. Remember, we just take our, let me actually maybe use the space up here. We're going to take our diagonal elements, 5 and -2. We're going to subtract lambda from those. Leave the other ones alone. And then we'll take the determinant of that 2 by 2 matrix. Of course, we get to then essentially cross multiply. 5 minus lambda times -2 minus lambda. Then we subtract -2 times 6, so we add 12. If we expand that out, we get lambda squared minus 3 lambda plus 2. And that can be factored as lambda minus 1 times lambda minus 2. All the problems we're going to be doing here are going to be nice and factorable. We go ahead and find eigenvectors corresponding to these. So I'm going to call the lambda 1, 1. That means I'm going to take our matrix here, subtract 1 from our diagonal elements. So 5 minus 1 gives us a 4. The 6 and the -2 are the same, and -2 minus 1 is a -3. Do some row operations. Of course, we can go ahead and divide that first row by 2, and then we can use that to cancel out the second row in its entirety. And of course, all we're trying to do is find some solution here as if we had a column of zeros. So this matrix times something equals 0. That'll give us an x1, which I'm not going to pick 1 for our free variable, for our second variable. I'm going to go ahead and pick the 2 so we don't have to divide by 2 later on. And that will leave us with a -3 for that first variable. So this is an eigenvector corresponding to the eigenvalue 1. Do the same thing for 2. So lambda 2 is 2. That's our second one from up here. Go ahead and take 2 from each of our diagonal elements. That'll leave us with a 3, 6, -2, -4. Again, I'll go ahead and divide my first row by 3. So I get a 1 and 2. And of course, I can use those to cancel out the second row. And now I'm just looking for an x2. This time I will go ahead and pick 1 for my second variable, leaving a -2 for my first variable. And now all I need to do is I need to take my lambdas and my x's, my eigenvalues and eigenvectors, and put them together into matrices. So my D is going to be the diagonal matrix with 1 and 2 as my diagonal elements. And my x, I need to make sure I put them in the same order as the order that I put my eigenvalues in. So the first one, lambda 1, being the 1 here, I need to put the x1 as my first column. And then I need to put my x2 as my second column. And that's really all there is to it. We found D and we found x. And you can check by hand, if you want to, that our matrix A, so 5, 6, -2, -2, is equal to the product -3, -2, 2, 1 times 1, 0, 0, 2 times the inverse of -3, -2, 2, 1. I'm not going to go through finding that inverse or doing this matrix product. You can do that by hand if you want to. Or you could actually even see that this matrix times this matrix, if you move that inverse over to this side, basically take A times X, you can show that's equal to X times D. That way you don't have to compute an inverse. But it'd be the same thing. Same kind of idea. Let's do a bigger example. So, part E. Same instructions here. We're still trying to find the diagonalization of A for this 3 by 3 matrix. That means we still go ahead and do this as an eigenvalue problem. Take our diagonal elements, subtract lambda from them. Everything else stays the same. Of course, we then have to actually expand this whole thing out. We do get a little bit lucky here. We have a lot of zeros in that first row. So we have lambda minus 1 times the 2 by 2, or the 2 by 2 determinant that we have here. So we have a lambda minus 1 times negative 1 minus lambda minus 3 times 1. And then, well, we have 0 and 0. So no other terms after that. Which means I'm also not going to distribute through my 1 minus lambda. Might as well leave that outside. If we expand this thing out inside here, it's going to simplify to lambda squared minus 4. And then we can factor that part as lambda minus 2 and lambda plus 2. So my eigenvalues are going to be 1, 2, and negative 2. And of course, since those are all different ones, we already know at this point that this is a diagonalizable matrix. We won't run into any problems because we're guaranteed at this point to have 3 independent eigenvectors. Of course, the wording of the problem already kind of guaranteed that, but it's nice to have verification of that. If I just gave you a matrix and asked you, can you find out if it's diagonalizable, or can you try to diagonalize it, you'd have to ask. You'd want to ask that question at some point. Do we know if we can keep going with this? So we'll start with 1. We're going to take 1 from each of our diagonal elements. So 0, 0, 0, negative 2, 0, 3, 1, 1, negative 2. Go ahead and do our row operations for this. Of course, the row of all zeros, I'm just going to put as my last row. And then I'm going to go ahead and put the 1, 1, negative 2 as my first row. Then I can use that 1 to actually cancel out the negative 2, and I'll be left with 2, negative 1. Again, because of that 2, I'm actually going to pick 2 for my third variable, because that will then leave 1 for my second variable, and then we can use this first row and find out that we get a 3 for that first one. Moving on to our second eigenvalue. So I'm going to go ahead and put 2 as my second one. Of course, then I subtract 2 from each of our diagonal elements. So the 1 becomes a negative 1. The other 1 also becomes a negative 1, and the negative 1 becomes a negative 3. Alright, so what happens now? Well, our first row, all we really need to do is multiply by negative 1. Then we can use that 1 to cancel out what we have in that. But since we have zeros here, it actually won't affect any of the rest of it. So we'd have a negative 1, 3, and a 1, negative 3. I'm going to put the 1, negative 3 as my second row. And then I'm going to use that to cancel out the third row. So our x2, now what do we have here? So if I pick 1 for our third variable, that's going to say a 3 for our second variable. But our first variable just has to equal 0. That's what this equation is saying. That means that 1 times our first variable equals 0. So we have 0, 3, 1. Finally, our third eigenvector It's not 3, unlike this pattern, it's negative 2. We're going to essentially add 2 to each of our diagonal elements. So we're going to have a 3, 3, then 1. Everything else stays the same. Again, this first row is actually kind of nice. We can divide it by 3 to leave a 1, 0, 0. We can then use that to cancel out the stuff in this first column, which actually doesn't affect anything in the other columns. Then we have 3, 3, and 1, 1. I'm going to put the 1, 1 first and use that to cancel out the 3, 3. So very similar to the last one. We have a 0 for that first. I'm going to put a 1 for the third. And then we end up with a negative 1 for the second. So these are 3 linear independent eigenvectors. We don't even have to show they're linear independent. The fact that they correspond to different eigenvalues already says that for us. So here are D. We're just going to take our eigenvalues, remembering what order we're putting those in, but that's why we labeled them as lambda 1 through lambda 3. Of course, we have zeros for everything else. X is going to be just our eigenvectors as our columns. 3, 1, 2, 0, 3, 1, and 0, negative 1, 1. And that's all we need to do. That's our answer. If you want to go back and check, you can check it. I would recommend checking that AX equals XD as the easiest way to check that without having to actually find that inverse. Though if you want to find the inverse, that's okay too. But that's all we're going to do there. Alright, one more problem. And then we'll move on to a whole nother topic in the next video. So here we have a matrix, a 3 by 3 again. We want to find the x and d as we did before. So we start off the exact same way. We're going to subtract lambda from each of our diagonal elements. Everything else is the same. And of course, we have to expand this whole thing out. This is actually, on its face, it's actually a lot more complicated than the previous one. We have the 1 minus lambda times, then it's 2 by 2, so we have 4 minus lambda times negative 3 minus lambda, then plus 12. That thing's then going to be, well, we're actually going to subtract 2 times negative 3 minus lambda minus negative 2 times 3, so plus 6. And then we have, well, minus 1 times 2 times 6 is 12, minus 3 times 4 minus lambda. And then we have to set that thing equal to 0. But if you actually expand everything out, this turns into negative lambda cubed plus 2 lambda squared, which if you go ahead and factor out a negative lambda squared, we get a lambda minus 2. So what do we have here? We have lambda equals 0 and lambda equals 2 as our eigenvalues. Let's start off with the lambda equals 2, because the lambda equals 0 is going to be repeated. This square means that it is of multiplicity 2. So that's going to be our possible trouble spot. Like I said before, on the previous one, the instructions here kind of imply that we won't run into a problem, but we don't know that for sure at this point. So, kind of mark that off. I hit the scroll bar, sorry. So our lambda 1 is going to be 2. That means we're going to take 2 from our diagonal elements. So they're going to be negative 1, 2, and negative 5. Of course, everything else stays the same. Going to use our row operations. Of course, might as well use that negative 1, just change the sign of it. So we have negative 1, negative 2, or sorry, we get this becomes a positive 1, then we have negative 2 and 1. Use that to cancel out the other things in that column. That'll leave us with a 3 and negative 2, and I'll use that to cancel out the other parts. So this is what we're going to get overall. Of course, that gives us an x1. Since we have the 3 here, I'm going to go ahead and pick 3 for our last variable, which will give us a 2 for our second variable, and ultimately give us a 1 for our first variable. So 1, 2, 3. Our lambda 2, and we're pretty much going to just say it's our lambda 3 as well, because it is a repeated eigenvalue. We just hope that we actually do have more than one eigenvector corresponding to it. But we're just going to look at the matrix that we started with. We're just subtracting 0 from our diagonal elements. And we want to know what happens to this. So we go ahead and do our row operations. Of course, we're going to keep that same first row. We're going to use it to cancel out the 2 and the 3 in that first column. But actually, what happens here? All the second 2 rows are just multiples of the first row. You might have noticed that from the beginning. If we just multiply that first row by 2, you get the second row. If you multiply by 3, you get the third row. So actually, everything aside from that first row cancels out. That means that both x2, or I shouldn't say x2, both the second variable and the third variable are free variables. And that's actually the key to making this whole thing work. So I'm going to pick 2 vectors where I'm going to just say let 1, 0 for the second 2 variables for the first one, and 0, 1 for the second one. If I do that for x2, I'm going to get negative 2 for our first variable. For x3, I'm going to get 1 for our first variable. Those are 2 vectors. They're both eigenvectors corresponding to 0, and they're independent of each other. Specifically because in the middle, in the second variable, 1's 0 and 1's not 0, and in the third variable, the first one's 0 and the last one's not 0. That guarantees that they cannot be dependent on each other. So we now have 3 linear independent eigenvectors for this matrix A, and that's what we wanted. So again, we're going to take our diagonal matrix to use these eigenvalues. So we have 2, 0, 0 as our diagonal elements. Now, it may not look necessarily too diagonal once we have 0 on our diagonal as our diagonal elements, but it still is a diagonal matrix. Everything else is zeros, and that's our diagonal matrix. Our x, in this case, we take our eigenvectors, making sure that we do put the 1, 2, 3 as our first column to be associated with the 2. Technically, we could switch the order of these without caring about it. It won't change anything. I mean, technically it would be a different x, but it would still actually satisfy the equation that we're trying to get of ax equals xd, or the equivalent of that. I'm going to go ahead and put my second column as negative 2, 1, 0, and my third column as 1, 0, 1. And you can go ahead and just check that if you take this matrix, multiply it by D, you get the same thing as if you took A and you multiplied it by X. And that's what we wanted. So, keep in mind, this might not have worked out as so nicely if we hadn't have gotten... Basically, the very fact that both these rows canceled out was the key. If the second row had been left with something like 0, 0, 1, this wouldn't have worked. We would no longer have been able to get 2 linear independent eigenvectors corresponding to 0, and our matrix just simply would not be diagonalizable, no matter what we do. So We will actually see an example of such a defective matrix in a later video. But that's all I want to do for the moment, and I'll leave that to, like I said, a later video. So I'll see you then.